Hello and welcome to our presentation on the comparison of spatial visualization techniques for radiation in augmented reality. I am McCall, leader of the Visualization and Interaction Research Group at the Luxembourg Institute of Science and Technology. This presentation is together with my colleagues Fintan and McGee, who led this work, and Joan Baixauli. Our study leads to 5 key takeaway points relating to the visualization techniques themselves and the underlying methodologies used in the study. These are that the spatial awareness mesh can be leveraged for real-time visualization. The points on the mesh can be colored to reflect the intensity of a field such as radiation. Various techniques are possible to balance visibility of the real and virtual. This is to ensure that the operative can continue to see the underlying environment, which is a safety requirement. Stencils can be used to allow participants to see the visualization as part of a pattern with gaps exposing the real world. A stencil can also be used to encode direction information, such as arrows. Transparency can also be used to allow the participants to more easily navigate through the visualization. In the user experiment, different visualization encodings were tested, however, no significant differences were found. This study consisted of 25 participants simulating a task in a room with multiple virtual radiation sources. This revealed no significant differences in time and error or preferences across all participants. However, we think that individual differences between the participants may play a large role. These individual differences require some further examination. However, the distribution of preferences for some key visual encodings was binary, with many participants either loving or hating it. This was reflected in the free text responses of the participants and helps explain the lack of significant difference in terms of preference overall, as well as other metrics. We also found that the choice of evaluation materials is important, or rather the methodologies used. Choice of questions plays an important role. Asking the wrong questions, for example, may obscure an interesting result. Due to the focus on situational awareness, we decided to adapt questions from established questionnaires. However, in retrospect, choices should have been more focused on our own specific experiment. First responders have to deal with incidents which include chemical, biological, radiological, or nuclear materials. While ultimately they may need to remove these sources, they may also need to gather evidence first. As radiation is invisible, they often use detection equipment to locate and identify the sources. During this process, often the initial team identifies the sources and another team searches for evidence while keeping their exposure to a minimum. Training with real hazardous materials is of course dangerous, expensive, and time-consuming. Using augmented reality in a training context is often quicker, safer, and cheaper, even when compared to simulated chemical type approaches. Augmented reality also provides the possibility for the radiation to be visualized as part of the training. The picture shown illustrates a number of the visualization options used in the study. During any training scenario, the user only sees one of these at a time. In order to support a training scenario, a number of requirements were identified. One, that the visualization should help to identify the safest path to follow. Two, that the radiation will be visualized on the surfaces around the sources, i.e. using the spatial awareness mesh to avoid adding extra clutter to the scene. 3. That the visualization should be responsive and support real-time updates of moving sources. 4. That the radiation must accumulate from multiple sources. And finally, 5. That it must be possible to allow the users to see both the physical world and the virtual radiation. We are using the HoloLens 2, as the optical see-through nature of the device means it is preferable for the first responder training, and the hardware automatically builds a spatial awareness mesh of the user's environment. Additionally, development is simplified by the Unity platform, and access to the spatial awareness data through Microsoft's Mixed Reality Toolkit is relatively straightforward. In order to meet the real-time responsiveness requirement, a GPU-based approach was adopted. Updating the color of the spatial awareness mesh is also conceptually simple using a shader attached to a custom Unity material. Three separate sets of shaders were created. The first for coloring a pixel based on accumulated radiation intensity. The vertex shader is quite simple, while the fragment shader calculates the cumulative radiation at a specific point, using an exponential drop of intensity based on distance, and it then maps it to a color on the input texture. A second set builds on this by including stencils which are positioned using triplanar texture mapping, and the third set builds on the stencil functionality, adding in orientation for arrows. Our implementation handles up to 10 sources, and we use the multiple compile functionality of Unity with pre-compile directives to avoid unnecessary computation when fewer sources are used. Full technical details, including pseudocode for the shaders, are available in the supplemental materials. 6 different visualization approaches were developed, including 3 that use stencils, one of which explicitly encodes direction. We used the Viridis color map for all approaches, as it is considered effective and is more resistant to red-green color blindness. Continuous is the base condition, and it uses the full Viridis scale to display radiation intensity. Transparent is similar to continuous, but the opacity is set to 33%. Banded visualization uses a Viridis scale divided into 8 distinct color bands to help users clearly distinguish the changes in radiation gradient. The circular visualization is the simplest stencil, where intensity is rendered on a circular pattern repeated across the spatial awareness mesh. The user can see the real world through the gaps between the circles. The hexagonal visualization has more consistent space between the stencils than the circular mesh. The hexagon texture is scaled so that the hexagons are of comparable size to the circles. Finally, the arrow visualization explicitly encodes direction by pointing away from the source. The direction of the arrow is based on the average combination of the sources. If a source is moved, the orientation of the arrows updates in real time. Our experiment simulates a simple object retrieval task. The participant entered the experiment room, navigated to a table, searched for an item, and exited the room, during which time they had to try and minimize their total radiation dose absorption. The room was split by a partition with 2 gaps for the participant to pass through. A playing card was chosen for the item as it is a recognizable item of a suitable size, and the user had to select the correct card from the 26 others on the table. This was done for 5 different layouts of 3 virtual radiation sources, for each of the visualizations, with each visualization being presented in a separate block. Each participant performed 30 trials, in addition to some training tasks. Virtual radiation source layout and visualization block order were randomized. For each trial, the time elapsed in seconds and the user position was recorded. In addition, the following metrics were then calculated. The cumulative radiation exposure during the trial in sieverts, the mean dose rate received in sieverts per hour, the mean distance to the nearest source in meters, the maximum dose rate received in sieverts per hour, and the time in proximity, or 1.5 meters, to the card table in seconds. The participants were asked to rate their visual spatial ability. This was to see if it had any impact on their performance. After each trial block, they were also asked to complete a questionnaire adapted from existing spatial presence and situation awareness questionnaires. In addition, 3 custom questions were added. These new questions focused on the perception of the real and virtual and the balance between the two. They were also asked to rank the visualizations and provide free-form responses. There were no significant differences between the different visualization approaches in terms of metrics, questionnaire ratings, or rankings. The arrows visualization approach resulted in the lowest cumulative radiation dose on average and the lowest average time. The arrow visualization also resulted in a smaller distribution of values for the time in proximity to the table. This is understandable, as the arrow stencil provides the least amount of spatial awareness coverage of all the visualizations. However, the differences are not large enough for any form of statistical significance. The visualization approach questionnaire data is somewhat consistent, particularly for the questions concerning awareness of the physical and virtual and the balance between the two. With respect to the rankings, there are still no significant differences, with both Banded and Arrow being joined first. The rankings are also consistent with the metrics and questionnaire result. Across all the metrics, there were no significant differences. While there are multiple metrics, many relate to radiation exposure, which is, in itself, a product of time and distance. All of the visualizations, even the base continuous one, were effective at keeping the participants away from the sources. While there were differences in time, there were not enough for cumulative radiation values to be affected to any significant degree. We did not find any significant differences within the questionnaire responses. In addition to the questionnaire responses shown, participants were also asked to provide free-form feedback. These prove invaluable for understanding some of the reasons as to why perhaps there were no significant differences. It is clear, for example, from the positive and negative comments concerning the arrow visualization that participants had a diverse range of views. It also provides insights about what participants saw as important features, with the ability to see the limits of the radiation being of interest to them. One comment even mentioned the possibility to see the card outside of the AR display of the HoloLens. This is despite the fact that participants were instructed not to do this. Other hardware devices may not have suffered from this issue, but these may also have suffered from other problems. So why were there no significant differences? Navigation in 3D space with visualizations is difficult, and there may be many confounding variables. For example, the experiment hardware may have caused issues, for example related to the transparency and contrast and the extent of the AR display. These were also complex environments with a large number of conditions, and ultimately there was a small effect size. Furthermore, the experiment session took place over an hour, and fatigue may have become a factor, despite the randomization of the block order. Two of the more popular visualizations, arrow and continuous, have binary distributions in terms of preference, with many people giving it a top or close rank and a bottom rank. It appears that these visualizations were either highly ranked or lowly ranked with little in between, making it difficult for the rankings to be differentiated. This would suggest that individual participant preferences may play a significant role. Two of the more popular visualizations, arrow and continuous, have a binary distribution in terms of preference, with many people giving them either a top or close to top rank or a bottom rank. It appears that these visualizations were either highly ranked or lowly ranked, with little in between, making it difficult for the rankings to be differentiated. This would also suggest that individual participant preference may play a significant role. So what lessons have we learned, and what recommendations do we have for future work? Firstly, we adapted the questions from existing questionnaires related to situational awareness and spatial presence. However, the questions we proposed ourselves concerning the balance of the real and virtual distinguished the visualization approaches better. We believe that the development of a standard situated visualization-specific questionnaire for evaluations is something that would benefit the community. Furthermore, the experiment duration can be an issue, with participants perhaps rushing the trials if they are no longer engaged. For most users, the experiments lasted around 1 hour. Reducing the number of conditions would help to reduce this further and perhaps make it easier to find statistically significant differences between the visualization approaches. In this study, non-domain experts were used. In future, we may look at using domain experts to see if this results in significant differences between the visualization techniques. The individual differences and preferences of users are also important. In terms of implementation, this may come down to providing an end user with multiple techniques to choose from, and the possibility to adjust parameters of a technique based on their personal preference. Thank you for watching our presentation, and if you have any further questions or wish to get in touch, please contact Fintan McGee at the email address shown on the slide.